Hey there, future chemists. Welcome to your go-to guide for absolutely acing SPM chemistry. Okay, before we get started, let's talk about supercharging your revision. You're going to want to scan the QR code you see on the screen, or you can just head over to www.mcqspm.com. It's an amazing platform for active learning, and it's packed with thousands of practice questions to really hammer home what we're about to cover. Oh, and you can also grab the MCQ SPM app from the Google Play Store. All right, let's dive right in. Electrolysis. Look, I get it. This is one of those topics that can really be a major headache for students in the chemistry paper. But trust me, today we're going to make it all click. So I'm going to let you in on a little secret. It's just one simple thing that makes this entire topic, well, honestly, it makes it easy. I mean, really easy to get. So think about an ionic compound when it's just a solid crystal. Picture this. All the ions are there, but they're like people in a completely packed lecture hall. Everybody is stuck in their seat in this super rigid, fixed structure. They just can't move around at all. But then, what happens when you crank up the heat and melt it? Or maybe you just dissolve it in some water? Well, suddenly, that boring lecture is over, and the dance floor is open. All those same ions are now totally free to move, to groove around, and, this is the important part, to carry an electrical charge from one place to another. Okay, so this is the absolute key. If you forget everything else from today, just remember this one thing. To conduct electricity, you need free-moving ions. That's it. No movement, no electricity. It is that simple. If those ions can't move, the circuit is totally broken. And that little light bulb in your experiment, it's not going to light up. Period. So what's the official name for these things? Well, they're called electrolytes. And that name was actually given to them way back in 1834 by the absolute genius Michael Faraday. He's the one who figured out that they don't just conduct electricity, they actually go through chemical changes while they do it. All right, so let's take a closer look. How does our little free-moving ion secret actually play out inside a real electrolytic cell? This is where all the cool chemistry starts to happen. Okay, so here's what a typical setup looks like. You've got an external power source, like a battery, and we use that to push an electric current through our electrolyte. And that whole process of breaking down the compound, that's what we call electrolysis. See the two electrodes? They're dipped right into the liquid and hooked up to the positive and negative terminals of the battery. So to make this super clear, let's use a classic example that you'll definitely see in your SPM papers, the electrolysis of molten lead-2 bromide. All we do is heat up the solid PbBr2, and bam, its ions break free from that rigid structure and start moving all over the place. Now this table is awesome because it shows exactly what's happening at each electrode. Just remember, opposites attract, right? So the positive lead-2 ions, they're going to be attracted to the negative electrode, which we call the cathode. When they get there, they gain electrons, that process is called reduction, and they form this gray solid, which is just pure lead metal. At the same time, the negative bromide ions, they travel over to the positive electrode, the anode. There, they do the opposite. They lose electrons, that's oxidation, and they form bromine gas. And you'd actually see that as this really distinct brown gas bubbling off. Okay, so now that we've got the basics down, let's talk exams. Let's look at how you can use this knowledge to tackle common questions and, more importantly, how to avoid those classic traps that examiners just love to set for you. All right, exam alert. Pay attention because this is a big one. You have to know the difference between a conductor, like a simple copper wire, and an electrolyte. They are not the same thing. As you can see here in a metal conductor, the electricity is carried by free-moving electrons. The metal itself doesn't change at all. But in an electrolyte, it's those free-moving ions doing all the work, and the substance itself actually decomposes. That is a massive, crucial difference. Okay, let's look at a super common scenario you'll find in Paper 1 and Paper 2 questions. Imagine a student sets up an electroplating experiment. They want to coat an iron ring with some shiny silver, but nothing happens. So what went wrong? Let's be detectives here and figure out what the problem could be. So if we look here, there are basically three main things that could have gone wrong. First, maybe they used the wrong electrolyte. If you use something that doesn't dissolve, like silver chloride, well, you're not going to have any free-moving silver ions to do the plating. Makes sense, right? Second, and this is probably the most common mistake I see, is getting the connections backward. The object you want to plate has to be the cathode, the negative terminal. And finally, the anode itself must be made of the metal you're plating with, so in this case, a pure silver bar. That way, it can dissolve and keep putting fresh ions into the solution. Okay, here's another one.
A real classic question that pops up all the time, and it's designed specifically to test if you really understand our big secret. You've got two beakers. One's got pure glacial ethanoic acid, and the other has dilute ethanoic acid. So which one is going to light up the bulb?
And the answer is the dilute ethanoic acid. So why is that? Well, because the pure stuff, the glacial ethanoic acid, just exists as molecules. There are no ions to move around. But the second you add water to it, those acid molecules ionize. They literally break apart into hydrogen ions and ethanoid ions. And what do you have then? Yep, free-moving ions. See, water is like the key that unlocks the ions. So at this point, you might be thinking, okay, this is great for passing my exam, but so what? Why does any of this matter in the real world? Well, let me tell you, electrolysis is a massive, super important industrial process. It affects our daily lives in ways you probably don't even realize. I mean, just look at the main uses here. Think about the aluminum in the soda can you're drinking from. How do we get that metal? We extract it from its ore using electrolysis. We also totally rely on it for purifying copper to get that super high-grade stuff we need for all our electrical wiring. And of course, like we just talked about, electroplating. It's what gives jewelry its shine and protects car parts from getting all rusty. Just wrap your head around this number for a second. 99.99%. The copper that's used in pretty much all our electrical wiring has to be 99.99% pure. Why? For maximum conductivity. Even the tiniest little impurity can make a huge difference. And how do we get it that pure? You guessed it, electrolysis. So, if there's one thing you take away from this entire explainer, let it be this one powerful rule. Remember, no free-moving ions, no flow of electricity. It really is that simple. If you're ever staring at an exam question and you're stuck, just ask yourself, are there ions and are they free to move? If the answer is yes, you're dealing with an electrolyte. So, now that you've totally cracked the code on electrolysis, I want to leave you with a little challenge. Think about this. Where else in your SPM chemistry syllabus does this fundamental idea of free-moving ions show up? Because mastering this concept here, it doesn't just help you with one chapter. It actually helps you unlock a ton of other areas in chemistry. Look, don't let this fresh knowledge just fade away. Put it to the test right now. Head back over to MCQ SPM, find some of those electrolysis questions, and really start building your exam confidence. Just keep practicing and you'll keep improving. You've got this.